Hello world, we're going to be doing a basic kinematics problem. Over here in the left hand corner, I have the three basic kinematics equations that you're going to be using, and I'm going to be denoting final velocity with just the regular v. So this first one says that the final velocity is equal to the initial velocity plus the acceleration times time. The second says final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in displacement. And the final one says that x minus x naught, which is the change in displacement, is equal to the initial velocity times time plus 1/2 the acceleration t squared. And bear in mind that all of these are vector quantities: velocity, acceleration, displacement. And in that regard, we need to specify a direction. So I'll choose my coordinate axis right now, and I will just say to the right is positive, to the left is negative. And bear in mind, I'm using this horizontal plane. The motion is inside one dimension. So here's my cube. My cube, it's going at 21 meters per second, and it slows down uniformly to rest in 6 seconds. And I want to know how far did my cube go. So first, I will mark this instant. I'll look at this as the instant that I start to slow down. I'll call this x naught. This is my reference point. And remember, your reference point, that's the point that you take as 0. That's where you're measuring from. So this is some distance traveled, and I'll call this point x. And I know when I started, I was moving at 21 meters per second. And I know that this entire ordeal took me 6 seconds. However, what's my final velocity? Well, I underlined this word here because this is a key word inside the problem. The same thing with uniformly, but we'll get to that in a moment. It said rest. Rest meaning no movement, meaning that my final velocity is equal to 0. And uniformly, that tells me something about my acceleration, because it says that I slow down at a constant rate. So that means that my velocity is changing, or it's decreasing at a constant rate, or uniformly. And that is what we call deceleration. And I can use any one of these beautiful equations over here to solve it. However, I like the last one because it's asking us to find how far did my cube travel. So it's asking us for a displacement. So we want displacement, and what do we have? We have initial velocity here, time here, and we want to find acceleration. And we can find the acceleration because over here we have final velocity, initial velocity, time, and we have 3 variables that we know and 1 unknown. So let's see if we can solve for acceleration. So V naught is equal to, V final velocity is equal to V naught plus AT. Now, with some magic, V minus V naught is equal to T, alakazam. And now I'm going to start plugging and chugging. So final velocity, what is this? This is 0. Initial velocity, this is 21. Time is 6. So I have negative 21 divided by 6 meters per second squared. Units are very, very important. And you can see that it's negative, and it makes sense because the object is slowing down. So the acceleration is acting in the opposite direction of the motion. And now I'm going to go ahead and I'm going to use x minus x naught is equal to v naught t plus 1/2 a t squared. So x naught is 0. This is 21 times 6. It's actually negative 1/2 21 over 6 times 6 squared. Now this is negative because I just took this negative out of this bracket and I moved it to the front. And let's start simplifying some things. This cancels out there. So I have 21.6. Let's do some 21 times 6. Let's do some quick math. That's 126. And then we have a half. This half cancels with this 3, with this 6, which gives me 3. So I'm left with 21 times 3. Actually, there's a, oh wow, that is beautiful. This is really beautiful. And if I factor out at 21, see, because I just pulled this 21 out of here, and I pulled it out of here. So if I distribute it, I've done nothing new. I still get the same thing back, which is just 21 times 3, which is a beautiful 63 meters per second. Smiley face. Sorry, 63 meters. Smiley face.